Hello everyone, welcome back to my channel. In this video, we are going to explore about chapter 10, light reflection and refraction, topics 10.1 and 10.2. Let me first introduce the topics and subtopics covered in this video. 10.1, reflection of light. 10.2, spherical mirrors. Under spherical mirrors, we have four subtopics, that is 10.2.1 image formation by spherical mirrors, 10.2.2 representation of images formed by spherical mirrors using ray diagrams, 10.2.3 sign convention for reflection by spherical mirrors, 10.2.4 mirror formula and magnification. Before entering in the actual content, let's understand the basic concepts behind our topic, that is introduction. Light is intimately involved with our daily lives. Many unique properties of lights are extremely fascinating. Here we will take one step closer to the wonders of light. All you know about light. Children, in your lower classes, you might have studied about what is light, is it? Light is a form of energy. Light always travels in straight line. Light gives a sensation of sightedness. Sun is the ultimate source of energy and it is also a natural source. We too have artificial sources of light as light bulbs, torches, etc. Light carries energy required to sustain life on earth. Like so many facts you have already studied and it was getting boring too, right? Here I would like to extend the standards and bring out some new stories or ideas about light. Let me introduce the next version of light for you. Here you go. All you must know about light is an electromagnetic radiation. Okay, then what is electromagnetic radiation? Electromagnetic radiation is a form of energy that is all around us and takes many forms such as UV rays, radio waves, microwaves, X-rays and gamma rays. Sunlight is also a form of electromagnetic energy, but visible light is only a small portion of electromagnetic spectrum which consists of a broad range of electromagnetic wavelengths where gamma rays have shorter wavelength and radio waves have longer wavelength. Hope you could see a colorful electromagnetic spectrum over here, and the visible light spectrum is a segment that a human eye can view. More simply, this range of wavelengths is called visible light. Typically, the human eye can detect wavelength from 380 to 700 nanometers. Next, nature of light. Light is an electromagnetic spectrum. Yes, just now we discussed sources of light are of two types, natural and artificial sources. Already we discussed. Now, luminous and non-luminous objects emits its own light. They are luminous objects and they do not have their own lights but reflects the light from other source or non-luminous objects. Example for luminous or sun, stars, light bulbs, etc. Likewise for non-luminous, moon and all the living and non-living things reflects light. Next one is transparent, translucent and opaque mediums. You already know these three basic mediums. With transparent medium, light can pass through it and all light can pass through it. Translucent medium passes partial light and opaque region passes no light. The next one is speed of light. In ancient times, many scientists believed that the speed of light was infinite. The Italian physicist Galileo Galilei was among the first to try to measure the speed of light. Later, around 1676, a Danish astronomer D. Romer became the first person to prove that the light travels at a finite speed. In the ensuing centuries, a number of scientists worked to determine the speed of light, but finally, in 1983, an International Commission on Weight and Measures let the speed of light. They set the speed of light in vacuum and air is 3 into 10 to the power of 8 meter per second. And next one is dual nature. Yes children, light has dual nature, which means in some experiments light behaves as wave, in some experiments light behaves as particle. Confusing, right? Let's understand in detail. Children, as you know, when a light travels through a transparent or translucent medium, light passes in straight line, fully or partially. But when an opaque object is placed in the path of a light, the behavior of the light changes and it bends around its edges. That is called diffraction. Know this point, the light bends. So far we studied light travels in straight line. But in this case, the light bends and has a flexibility too. Only a wave can behave like this. They started the debate on nature of light, where Newton demanded light is a particle, while Huygens demanded light is a wave. Finally, after long discussions, fights and researches, it is proved that light is neither a wave nor a particle, but it has dual nature. So that's it. To know more about this, check out the last part of this video. Optics and introduction. Optics is the branch of physics that deals with behavior and properties of light. Two types of optics: geometric optics or ray optics, wave optics or physical optics. Light is considered to travel in straight line under geometrical optics, where light is considered as an electromagnetic wave under wave optics. So while considering the light as in particle nature or straight line path, when a light travels in a straight line path, then the reflection, refraction, dispersion and scattering are the phenomenon involved in it. While the light is considered as in wave nature, we will be discussing about the phenomenon like interference, diffraction and polarization. In this chapter we will focus on ray optics, while wave optics you will learn at higher classes. The first one is geometrical optics. Geometrical optics is based on two basic laws: the laws of rectilinear propagation and the law of reflection. Here you can see how to represent a light ray. It can be either a ray of light or a beam of light. A single straight line with arrow represents the ray of light, where a group of straight lines with arrows represents a beam of light. A beam of light may be parallel beam, convergent beam or divergent beam. Picture tells you the same. A parallel straight lines are called as parallel beam. When all the rays come to meet at a point is called as divergent beam. When all rays gets dispersed at a point is called as divergent beam. So the next, reflection of light. The literal meaning of reflection is bouncing back. So reflection of light means bouncing back of light to the same medium. Okay. Where it happens? When a light ray falls on a shiny or smooth surface, then the reflection happens. Example, mirrors. When a ray of light hits on a mirror, it reflects. You can see the picture at this moment, which shows you the same. The ray which falls on the mirror is the incident ray. The ray which gets bouncing back is reflected ray. When you draw a normal line, that is a perpendicular line, one can easily mark the angles it produced. The angle between the incident and normal is angle of incidence. The angle between the reflected ray and the normal is angle of reflection. Always for a plane mirror, angle of incidence is equal to angle of reflection. The next one is laws of reflection. There are two laws of refraction. The first one is the incident ray, the reflected ray and the normal all lie on the same plane. The second law is always the angle of incidence is equal to the angle of reflection. There are two types of reflection. The first one is regular reflection. The next one is irregular reflection or diffused reflection. If a parallel beam of light falls on a very smooth, silky, shining surface, all the beam of rays gets reflected back. So I is equal to R. But for the second case, that is irregular reflection, when it's not falling on a smooth surface, rather it is going to have a rough surface, and if it's going to incident, all the beam of light is going to incident on the particular surface, then the reflection will be like this. You could see the deflection or diffused reflection right now. But in this condition also, I is equal to R. Under reflection, all the reflecting surfaces will oblige the laws of reflection. All about mirrors. Mirrors, how it's made? Any idea, children? Mirrors are made by silvering or spraying a thin layer of silver or aluminium onto the back of a glass sheet. To protect the silver layer, the other layers are used. Hope you could see the same in the picture. So first a normal glass sheet, and over that a silver coating is given. In order to protect that silver coating, a normal thin layer of copper and a paint coating is given. So that's how a mirror is made. Since silver is very expensive, the mirrors cost high, and high definition mirrors are produced with that. But cheap mirrors are just coated by aluminium. Okay, now there are different types of mirrors. Mirrors are of two types. One is plane mirror, next one is spherical mirror. Under spherical mirror, we have two types of mirror. One is concave, another one is convex. We will explore one by one in detail. First, the image formation of a plane mirror. If you are going to stand before a mirror, you will be the object, and the replica of yours will be your image. Here you can see how an image is formed by a plane mirror. An object and an image. How the incident ray flows, how the reflected ray gets back from the image. You could see in this picture. The next one is characteristics of plane mirror. It's very, very important. It will always produce a virtual and erect image. The size of the image is equal to the size of the object. Which means, if you observe your image standing in front of the plane mirror, its size will be equal to your original size. That is, the image size is equal to the object size. Previously, I told you virtual and erect. What do you mean by an virtual image? The images which cannot be captured on the screen is called as the virtual image and is always erect in nature. The next one is the image formed is as far behind the mirror as the object is in front of it. So if you're going to move in front of the mirror, accordingly your image also will be moving. If you're going to move back from the mirror, accordingly your image also will be moving. That is what the concept. The last one is image formed is laterally inverted. If you raise your right hand, your image rises its left hand. That is called as lateral inversion. Okay. Now, spherical mirrors. How would the images be when the reflecting surfaces are curved? Let's explore by this activity. Take a large shining spoon. Try to view your face in its curved surface. Do you get the image? Is it smaller or larger? Move the spoon slowly away from your face. Observe the image. How does it change? Reverse the spoon and repeat the activity. How does the image look now? Compare the characteristics of the mirror on the two surfaces. What you will get, children? Of course, the curved surface of a shining spoon is considered as a curved mirror. The most common curved mirror is a spherical mirror. In a spoon, the curved inward part is concave, then the curved out part is convex. The reflecting surface of such mirrors can be considered to be forming a part of a surface of a sphere. Such mirrors are called as spherical mirrors. Let's understand them in detail. Next one is spherical mirrors. How it's made? Any idea, children? Yes. When a glass sphere is silvered one side, we get a curved mirror. Before we move further on a spherical mirrors, we need to recognize and understand the meaning of few terms. That is P, pole, C, center of curvature, R, radius of curvature, and XY, principal axis. First word is pole. The center of the reflecting surface of the plane mirror or an spherical mirror is called as pole. So here you can see two pole points in this picture. The next one is the reflecting surface of a spherical mirror forms a part of a sphere, and this sphere has a center, and that is called as center of curvature, that is available for both the mirrors, for concave as well as convex. But note it down, children, for a concave mirror it is present in front side of a mirror, and for a convex mirror the C point is present at its back. The radius of the sphere of which the reflecting surface of a spherical mirror forms a part, and that is called as radius of curvature. That is, radius of the sphere is nothing but the radius of curvature. That is also available for both the mirrors. The last one is imaginary straight line passing through the pole and the center of curvature of a spherical mirror is principal axis. So this principal axis is available for both the mirrors. Have a look at that. Let us understand a very important term related to mirror through an activity. So here comes that. Hold a concave mirror in your hand and direct its reflecting surface towards the sun. Direct the light reflected by the mirror on a sheet of paper held close to the mirror. Move the sheet of the paper back and forth gradually until you find the paper sheet a bright short spot of light. Hold the mirror and the paper in same position for a few minutes. What do you observe? Any guesses, children? Yes, heat is produced due to the concentration of sunlight ignites the paper. The distance of this image from the position of the mirror gives the approximate value of focal length. Let's try to understand this observation with the help of a ray diagram. Here you can see two ray diagrams of spherical mirror. The first one is a concave mirror and second one is a convex mirror. Imagine a large number of rays coming from an infinite source and falls on an reflecting surface of both the mirrors. For a concave mirror it gets converges, and for a convex mirror it gets diverges. Thus, we can define what is principal focus. So the principal focus of a concave mirror is defined as when a beam of light passing parallel to the principal axis, after getting reflected by a concave mirror or a converging mirror, it gets converges at a point on the principal axis, and that point is called as principal focus of a concave mirror. It is represented by capital F. Now, principal focus of a convex mirror. When a beam of light rays passing parallel to the principal axis, after getting reflected by a convex or a diverging mirror, it seems to be coming from a point on the principal axis, and that point is called as principal focus of a convex or a diverging mirror. That is also represented by capital F. Now, the distance between the pole and the principal focus of a spherical mirror is called as focal length. It is represented by small f. And lastly, the diameter of the reflecting surface of the spherical mirror is called as aperture. So in the diagram you can see the length of the reflecting surface of a concave or convex mirror is marked as m and n, and that is called as an aperture. While discussing about spherical mirrors, we should not forget the concept of spherical aberration. So what do you mean by that? When large spherical mirrors is used and if the light falls on it, they converge to many focus. As a result, a blurred image is formed. This effect is called as spherical aberration. This can be solved by using a parabolic shaped mirror. Here you can see the pictures of that. When a spherical mirror is used, it produces many focal point. When a parabolic mirror is used, there is only one focal point. So the spherical aberration is nullified by using a parabolic mirror. Hope the pictures at this moment makes you clear. For a spherical mirrors of small apertures, the radius of curvature is found to be equal to its focal length. That is twice of its focal length. That is R is equal to 2f. Note down guys, this is the first formula you are learning in this topic. R is equal to 2f. Next, image formation by spherical Mirrors. You have studied about the image formation by plane mirrors. You also know the nature, position and relative size of images formed by them. How about the images formed by spherical mirrors? How can you locate the image by the spherical mirror like concave mirror for different position of the object? Or the images formed as real or virtual, or the enlarged or diminished or of same size? Let's explore. Here you can see the cases. What happens to the image when the object is placed before a plane mirror and a curved mirrors. Since plane mirror has a flat surface, its image is of same size. But in a case of a spherical mirror or curved mirror, since they are curved in nature, whenever the object is moved front or back of the mirror, we get different sizes and nature of images. Hope the picture helps you in understanding. In order to plot an image formed by the spherical mirrors, we need to follow certain rules. So the first rule is, when a ray of light passing parallel to principal axis after getting reflected by a concave or convex mirror, it gets always passing through the focus. So for a concave mirror, you can see a ray of light coming parallel after reflection passes through the focus. In the next case, when a ray of light coming parallel to the principal axis, after reflection, it seems to be coming from the focus. Since for a concave mirror, the C and F points comes on the opaque region, we are supposed to plot like this. The second rule is, when a ray of light is passing through the focus, it will be always parallel to the principal axis after reflection. That's what this diagram explains. That is, for the first case, for a concave mirror, when a ray of light passing through the focus, after reflection, the reflected ray moves parallel to the principal axis. For the second case, that is for a convex mirror, when a ray of light falls through the focus or it is passing through the focus, imagine it's touching the focus, then it will be parallel after reflection. That's what's shown here. For the third rule, when a ray of light passes through center of curvature, it retraces its path, which means that it follows the same path. That's what the diagram says. And the last one is, when a ray of light incident obliquely to the principal axis, it will reflect on the same angle. That is, what do you mean by an oblique angle? Any slanting angle. If a ray of light hits on the pole, in what angle? The same angle the reflected angle will be. That's what the fourth rule. So hope you understood with all these pictures. Among these four rules, any two rules can be used to plot an image. When two rays after reflection meets at a point, then that point is the image formation point. Here we go with the table for different position of object in front of a concave mirror. Now look the candle picture, children. This candle picture, I have placed the candle in different places. Like first it is at infinity. Anyhow we cannot plot infinity, so I have just marked as infinity. The next one is, the next position is beyond C. The next position is at C. The next position is between C and F. The next position is at F. And the last position is between F and P. Like this, step by step, if I am going to move the object, what will be the position of the image? Children, this table somehow you have to memorize to draw the image formation. Let me teach you an easy way. First position is at infinity. So when an object is placed at infinity, the image will be formed at the focus and vice versa. Here I have represented that by a red color box. So whenever you are placing an object at infinity, the image is formed at focus. Likewise, when an object is placed at focus, the image is formed at infinity. That's what vice versa. The second case is, position is of an object is beyond C. When an object is placed beyond C, the image is formed between C and F. Likewise, vice versa, if an object is placed between C and F, the image is formed beyond C. So that has been marked by black color box. So both the cases are vice versa cases. And the third one is at sea, at sea. So whenever an object is placed at sea, the image is also formed at sea. So both are of same positions. And the last position is when an object is not even at the focus, that is between F and P, the image will be virtual and formed behind the mirrors. For a curved mirrors, always the images will be formed in front of the mirror till first 5 cases. The last case alone, that is if an object is not even at the focus, the image will be formed behind the mirror. When an image is formed behind the mirror, then that type of image is called as virtual image. Okay, now the next column, moving on to the size of the image. So the first two boxes I've been marked with an yellow color box, that is first two columns or rows. If you see, highly diminished, point size or diminished. And the next one, if you see, that is same size, the mid one is same size because same position the object and image is present. And the last 3 cases are fully enlarged. So the first 2 cases is diminished and the last 3 cases are enlarged. If you see the word as infinity anywhere in the position of the image or in the position of the object, you have to add a word highly. So in the first case, infinity is present. So they have added highly diminished. Likewise, in the fifth case, infinity is present. So in that particular case, highly enlarged. So that's how we have to understand. And the nature of the image. The first 5 positions will have real and inverted images as nature. That is, for the first 5 cases, the image is formed on the front of the mirror. For the last case alone, it is virtual and erect, so the image is formed behind the mirror. So an concave mirror can produce both real and virtual images. Using the rules studied before, when we plot for the first position, that is at infinity, we need to draw the 2 rays coming from infinity. When 2 rays coming parallel, it always passes through the focus after reflection. The 2 reflected rays meets at a point. And here in this case, the 2 reflected rays meets at F. So that is the image formation point. Hope you understood the first ray diagram. Second one is beyond C. So the 2 rays coming from the object, one passes parallel and the other passes through C. After reflection, they both meet at a point between C and F, and that is the image formation point. At C, the 2 rays coming from the object, one passes parallel, so after reflection it passes through the focus, and another through focus passing parallel. These 2 reflected rays meets at C, so the image formation point is at C. Like this, we can draw for the next 2 positions, that is between C and F and at F. Now comes the last position, between F and P. If an object is not even at focus, we cannot expect a real image. So by following the rules, if we extend behind the mirror, we get an enlarged erect image, and that is nothing but the virtual image. So that's how one can plot the image for concave mirrors. So next comes uses of concave mirror. Here you can see a solar cooker or furnace. In that solar cooker, the reflecting surface is made up of a concave reflector, where the center part is the focus part of that particular cooker where the vessel is placed. The vessel consists of food that to be cooked. So how does it work? When this particular setup is placed in front of the sun, where sun is the actual object position, from the sun the light rays comes and it reaches a solar cooker, and since it is made up of a concave reflector, all the rays of sun is getting converged at a point, and that point is the focus point. In that focus point only the cooking vessel is placed so that the food is getting cooked. So that's how the solar cooker works. Next, This type of mirrors, that is concave mirrors, for used for different purposes like a dentist usage mirror, shaving mirror and a makeup mirrors. If you go for a dentist visit, he will be having a spatula like thing which has a mirror in it. That is nothing but a concave mirror. It is placed near to the decayed teeth in order to examine something fault in that particular teeth. So when that mirror is made up of a concave mirror, it gives an enlarged image. So this is applicable for the positions of an object is placed between F and P. And next one, this mirror is also used in headlights of the car. That is headlights or the searchlights as a concave reflectors, where the bulb should be placed at focus so that it produces a parallel beam of light. So that's all about a concave mirror. Hope you understood. The next one is convex mirrors. Now the image formation for a convex mirror. Convex mirror has only two portions of the objects because the F portion and the C is all placed at the opaque region. So the first portion of the object is infinity and second portion is between infinity and P. As you already know, when an object is placed at infinity, the image is formed only at F, that is behind. And the next one, when an object is placed between the infinity and P, the image is formed between F and P behind the mirror. So this mirror always produces image behind the mirror, that is a virtual images are formed at a diminished size. So let's see the image formation diagrams. Using the rules of a convex mirror, if we are going to plot first position at infinity, the two rays coming parallel, after reflection gets diverged, but it seems to be coming from the focus. So F is the image formation point. The next case, when one ray coming parallel, so it always seems to be coming from focus. The other ray that passes through the C, so it retraces its path. Both meet between P and F. So that is the image formation point. Now the uses of convex mirror. There you can see the uses of convex mirrors, that is, it is used as a rear view mirrors in order to produce a wider angle view, and also used as a vigilant or road safety mirrors in order to monitor the public. So that's how these mirrors are used in real lives. So that's the end of convex mirrors. So next comes mirror formula and magnification formula. Under spherical mirrors, we will learn what is the relation between the three terms, that is U, V and F, where U stands for object distance, that is the distance between the object and the pole, and V stands for image distance, that is the distance between the image and the pole, and the last one is F, small f stands for focal length. They are related by 1 by F is equal to 1 by V plus 1 by U. In order to find the magnification of the image, we have to use a formula M is equal to H dash by H or minus V by U, where H dash is nothing but height of the image and H is nothing but height of the object, or minus V by U. Note down children, this minus is already existing in the formula. So here you can see how to calculate the magnification for a plane and a concave mirror. Hope this particular slide will help you for the same. Our next one is sign convention. While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign convention that is called New Cartesian sign convention. In this convention, P is taken as origin and principal axis is taken as x and x dash. If you divide a perpendicular line at the point P, easily we are able to measure the datas. So the sign convention rules goes like this. That is, all the distances measured parallel to the principal axis on the left side is considered as negative, on the right side is considered as positive. The object is placed only at the left side. All the distances are measured with respect to the pole. All the distances measured perpendicular to the principal axis above is taken as positive and below is taken as negative. This is a very important sign convention rules. Please make a note of it, children. So this one is for a concave mirror. So by using the rules whatever we have studied before, by applying the rules we can write the sign values for the measurable quantities like U, V, H, H dash, M, F and R. With these sign values we can solve any numerical given related to this particular topic. And the next comes convex mirror. This one is for convex mirror. Hope you noted, guys. These sign convention are applied in mirror formula to solve the numericals. So that's the end of this video. Hope you understood. Next comes some knowledge quest and followed by follow up. Watch it and do it yourself.